Hello, welcome to the video, and in this lesson we are going to talk about some particular multivariable distributions. Well, one in particular, and then the next video will do the next one. In your first course, you learned many particular distributions, single variable distributions, right? You learned the binomial and the hypergeometric and the negative binomial and the geometric and the Poisson and the continuous distributions, the exponential and the uniform and the normal. And so there's many distributions. We are going to learn two multivariable distributions, and they are going to be the multinomial distribution, which is going to be the kind of extension of the binomial. And in the next video, we're going to look at the bivariate normal distribution. And I'll just say a quick word about the multivariate. So two variables versus more than two variables. We're going to really look at the two variable case as far as the normal distribution, as far as that normal distribution goes. So let's start with the multinomial distribution. And as I said, this is an extension of the binomial. So if it's an extension of the binomial, let's refresh our memories on the context of the binomial. And then we'll see how that can be extended to more than two, right? Binomial two, multinomial many. So the binomial experiment, or the set of conditions that describe a binomial experiment, a binomial situation, are the following. So there are n independent trials of whatever it is you're doing, flipping a coin or whatever. Each trial for a binomial results in exactly one of only two possible outcomes. And typically for the binomial, those are called success and failure. The probability of success is p. And therefore, since there's only two, the probability of failure is the complement, is q, which is 1 minus p. But said another way, which is going to be useful in the multinomial, if you add those two up, because those are the only two categories, p plus q must give you 1. And x, the variable, is counting the number of successes. It's counting the number of successes in the n trials. So x could be, well, there could be 0 success, 1 success, 2, all the way up to n successes. And you don't need to count the number of failures, because why? Well, the number of failures is n minus the number of successes, because there's only two. So if all of these conditions are met, then x follows a binomial distribution with parameters n, the number of trials, and p, the probability of a success. And the mass function for x, little p of x, was the following. It was n choose x, p to the x, q to the n minus x. And this coefficient here is very often called the binomial coefficient, and this is the way you calculate it. N choose x is n factorial over x factorial n minus x factorial. Now, again, just like this up here, p plus q equals 1 is not how it's usually formulated for a binomial. For a multinomial, that is going to be useful. The same thing here, right? We write x and n minus x. But x is the number of successes that we know. N minus x is the number of failures. We're actually counting the two categories. And if you notice, those two, of course, since there's only two, they sum to n, the number of trials. So if we go then and look at the multinomial experiment, you also need n independent trials. But now each trial results in exactly one of k. And the binomial k was 2, right? K is 2. For a multinomial, we allow more possibilities, and those outcomes are often called the categories, right? So in a binomial, success and failure are the two categories. The probability of an outcome in category I is P sub I, right? So this is our first category in the binomial, so this, right, this is the probability. We didn't have to give the other one because there are only two. But if there are I different categories, we need to give, no, there are K different categories, then we have to give the probability for each one. That's not quite true. We could give up to K minus 1 and we could deduce the last one. But we, in the multinomial, give all K of them and have the restriction that they must sum to 1, which is the same restriction that is in the binomial, but not usually phrased that way, right? The total probability must be 1, so the probability of all those categories must land up or add up to being 1. If xi measures not the number of successes, but there are more than two categories, so it measures the number of outcomes in a category, right? X sub I measures the number of outcomes in category I during the n trials. So x sub I could be from 0 all the way up to n. But then, of course, just like the number of successes and the number of failures had to add to n, the number in each category has to add to n. And then, if these conditions are all met, then x1, x2 to xn, xk are jointly distributed discrete random variables with joint probability mass function. So the probability of x1, x2 up to xk is just like any mass function, the probability that x1 equals x1, x2 equals little x2, and so on and so forth. It is this is the multinomial distribution. It is n factorial over x1 factorial times x2 factorial all the way up to xk factorial times the product of the probabilities to the number in each category, right? And so you have to have that each of those little xi's is between 0 and n. The sum of the little xi's has to equal n, and the sum of the probabilities has to be 1. So if we compare that with the binomial, can I fit them on the same screen? Right, the same thing. Instead of the binomial coefficient, you have this, which is often called the multinomial coefficient. So we'll talk about that more in just a second. You've got the product of all the probabilities, times, not times, but to the power of the number of outcomes in each category. It's exactly the same thing with just more categories. So this coefficient is sometimes, it's called the multinomial coefficient, and it's sometimes written that same kind of choose notation where it's n choose x1 comma x2 all the way up to xk, but this is the way that it is calculated, and you may have seen that before in your counting unit in the previous probability course. So let's just do one example then using the multinomial distribution, and then in the next video, we'll look at a continuous example for the bivariate normals. So let's look at this example. So the following table gives us percentages of adults, those 18 years and over, in different age groups, right? So we have 1, 2, 3, 4, 5 different age groups with associated percentages, 18, 23, 16, 27, 16. If a random sample of 5 adults is chosen, so a random sample tells us that those are taken independently. If a random sample of 5 adults is chosen from the population, find the probability that the sample contains 1 person from group 1, 2 from group 2, and 2 from group 4. So we are in a multinomial situation. We are counting the number of individuals from 5 different categories, and we are taking a random sample. N is equal to 5 trials, right? We have K is equal to 5 categories, and incidentally, N is equal to 5. Now, they don't need to be the same. They don't need to be the same. They can be different. They can be different, but in our example, they are the same. K categories, N trials. And we are looking to find the probabilities as described here. So we are letting xi, right, x1 through 5 be the number of people from groups 1 through 5, those age groups up there. Then x1 through x5 follows a multinomial with n equals 5, and, right, there are 5 categories. Here is the n, 5n factorial over 1, 2, 3, 4, 5 variables factorial here, and there are our probabilities of each group, the probabilities, the percentages from the table, to the appropriate powers, to the powers, the number of individuals. So we are looking from 1 person from group 1, 2 from group 2, and 2 from group 4, which means that we are looking for none of them from group 3 and none from group 5. So plugging in those values, right, that's x1, x2, x3, 4, and, oops, I've misaligned something, x1, x2, x3, x4, x5, there you go. You plug in those values, that is just something that you can calculate, and you get your answer here, the probability, based on not success and failure, but on different outcomes in different categories with different probabilities. So that is the multinomial. Now there is more to it than that. One can look at the conditionals and the marginals and all that sort of thing, but we are going to just leave it there with the straight up multinomial calculation, and in the next video we'll go and talk about the continuous case of the bivariate normal or jointly normal random variables.